Welcome to the 10th episode of the Spacetime Cafe. Patterns in primes, structure, entropy, and the nature of intelligence. Imagine a universe encoded in prime numbers that don't just underpin mathematics, but secretly govern the very laws of physics and artificial intelligence. What if the chaos we see around us hides an elegant structure, waiting to be discovered through the lens of primes? Dive into the mind-bending intersection of mathematics, physics, and artificial intelligence as we explore how prime numbers shape the hidden structure of reality. Discover the profound connections between prime gaps, entropy, neural networks inspired by Hamiltonian mechanics, and the elusive Riemann hypothesis. From the granular mysteries of modular quantization to the elegant abstractions of category theory, we'll unravel how deeply prime numbers underpin the universe's architecture. Prepare for an intellectual odyssey that redefines what you thought you knew.
Okay, so have you ever noticed how the most mind-blowing advances happen when totally different fields collide?
Yeah, it's like they suddenly realize, oh wow, we've got so much to learn from each other.
Imagine physics and hardcore math and then AI, all of a sudden they're all talking.
And that's exactly what we're diving into in this deep dive.
It really is. We're going deep, way beyond the buzzwords, to see how these mathematical and physical ideas are being baked into the core of advanced AI. We've got research here on how energy flows in neural networks to the elegance of category theory in AI. And then we even have how a theorem from physics, Noether's theorem, can totally change how AI learns.
There's some really dense stuff here.
Yeah. So our mission is to pull out the truly mind-blowing insights without getting lost in the jargon.
Yeah, we want those aha moments to really hit home.
Exactly. And the thing is, these aren't just some dusty academic theories. This is the foundation for the next wave of truly intelligent systems. So if you're fascinated by how complex systems work and how different areas of knowledge connect, you are going to love this.
Absolutely. So where do we even begin with all this?
Let's start with something you can almost feel, right? Physics-informed neural networks.
Okay, yeah.
Specifically, how the principles of Hamiltonian mechanics and this thing called symplectic geometry are leading to AI models that are not just smart, but also more robust and easier to actually understand.
So Hamiltonian mechanics, at its core, it's a way to describe physical systems through this lens of energy. And that's captured by this thing called the Hamiltonian function.
Okay.
So in a closed system, the total energy has to stay constant. And that's a big deal, right?
Yeah.
So the way the system changes over time is actually controlled by these things called Hamilton's equations, which link the changes in the system's position and momentum to this underlying energy function.
Okay, I think I'm following. So let's take a simple pendulum swinging back and forth.
Sure.
The Hamiltonian describes its total energy, a mix of its kinetic energy when it's moving and its potential energy when it's at the top of its swing. And then Hamilton's equations tell us exactly how that pendulum's speed and position are going to change over time, making sure that the total energy always stays the same.
Precisely. It beautifully captures this dance between motion and energy.
Okay, so how do we actually take this really elegant physics and then plug it into AI?
That's where Hamiltonian Neural Networks come in, or HNNs for short.
Okay.
The idea here is to use a neural network to learn this Hamiltonian function directly from data.
Directly from data.
Yeah, so instead of programming in all the physics by hand, you feed the network with observations of how the system actually behaves.
Okay.
And from that, the network figures out this energy function that's driving that behavior.
The AI isn't just predicting what happens next. It's actually learning the energy rules that shape how the system works.
Exactly. It's going deeper, getting at the underlying principles.
That's pretty amazing. What's the big advantage here? Why go through all this trouble?
The main advantage is that these HNNs, they naturally learn and respect this principle of energy conservation.
Okay.
You don't have to tell it, hey, keep the energy constant.
Yeah.
It just emerges naturally because of how the network is set up to learn this Hamiltonian. And this leads to predictions that are much more stable and realistic.
Especially when you're trying to predict far into the future. Right?
Exactly. Think about it. If your model understands that the total energy in a system has to remain constant, its predictions are going to be much more grounded in reality.
Yeah, that makes total sense.
Yeah.
So do these HNNs, do they actually work on real-world problems?
They do, yeah. And we've seen successful applications in some pretty fundamental physics problems, like modeling the two-body problem.
Like planets orbiting a star.
Yeah, exactly. Even modeling the swing of a pendulum just from looking at video pixels. And they've also been used to understand how those mass spring systems behave.
Wow.
But the real excitement is their potential for even more complex domains like celestial mechanics with multiple bodies interacting, or simulating quantum systems, understanding fluid flow, and even diving into molecular dynamics.
Okay, so we're talking about some really complex stuff.
Yeah, and in all these areas, getting the energy conservation right is super important for accurate simulations. Imagine you're trying to predict where a satellite's going to be way out in the future,
Okay.
and you're using a standard neural network trained on short-term data. It might not get it right because it doesn't really understand this idea of energy conservation. It might show the satellite like gaining energy out of nowhere, which would make sense. But in HNN, because it learns the Hamiltonian, it respects that constraint, and that leads to much more reliable predictions.
Wow. So an AI could help us simulate incredibly complex systems much more accurately just by learning their fundamental energy rules.
That's the hope, and it's a pretty exciting prospect.
It really is.
Okay.
Okay, so that's HNNs and the power of energy conservation. Now let's talk about symplectic neural networks, or SympNets.
Okay, so SympNets, they take these ideas even further.
Okay.
HNNs focus on energy, right?
Yeah.
SympNets are all about preserving something called the symplectic structure of these Hamiltonian systems.
Okay, and that is?
Think of it like preserving the volume in something we call phase space.
Phase space.
Yeah, it's like this abstract space that holds both the positions and the momentum of all the parts in a system.
Okay, so it's not just the total energy that's conserved, it's also the overall shape of how the system's state evolves in this abstract phase space.
Exactly. And this ties in really nicely with what we call geometric integrators. These are special numerical methods that physicists and mathematicians use to simulate these systems. They're designed to conserve these geometric properties, including the symplectic structure.
Okay.
So SympNets are essentially embedding these integrators right into the architecture of the network itself.
So it's like building the rules of how physical systems evolve directly into the DNA of the neural network.
That's a great way to put it. And because of this, these SympNets are really good at learning complex dynamics.
Wow.
And there are even newer time-dependent SympNets like SympFlow, which can give us a continuous time view of this symplectic evolution, which is really useful for making predictions at any point in time.
Oh, very cool. And you mentioned before that these architectures can even be combined with meta-learning.
Yes. This is where it gets even more interesting. We have frameworks like MetaSym, which combines the power of these SympNets with meta-learning techniques. It allows the model to basically learn how to model these systems even better by leveraging knowledge from similar systems. And what's really neat is that it can handle both conservative forces like gravity, where energy is conserved, and dissipative forces like friction, where energy is lost, all while respecting that symplectic structure.
So it's basically learning to model like a whole family of related physical systems.
Precisely. It's understanding the common threads that run through them.
Very cool. Now, you also mentioned integrating these symplectic integrators directly into the training process. How does that work?
This is a pretty clever technique, and it's especially useful for systems where the Hamiltonian is what we call non-separable.
Meaning what?
It means you can't easily split the Hamiltonian into separate parts for position and momentum. Now, traditional symplectic methods sometimes struggle with these systems.
Okay.
But researchers have figured out how to use the same integration method for both simulating the system forward in time and for that backward pass during training. And they do this by leveraging this mathematical property called self-adjointness.
Okay. And this means you can use the same tool for both building and refining your understanding of the system.
Gotcha. But you also mentioned a challenge with something called implicit integrators.
Many of the more powerful integrators are implicit, which means figuring out the next state of the system needs both the current state and the one we're trying to predict. This makes things a bit trickier computationally.
Okay.
So techniques like predictor-corrector methods are often used. They provide a good initial guess for the next state, which speeds things up.
Makes sense. What are the big advantages of all this complexity? Why go to all this trouble to integrate these specialized integrators?
For one, they're really good at preserving chaotic invariant sets, the underlying structures within chaotic systems, even when you're using large time steps in your simulation. And that's something that most standard methods struggle with.
Plus, they show almost perfect energy conservation over long periods. And when you build these properties into the neural network training, the resulting models need less data to learn and tend to generalize much better to new situations.
So we're getting AI that's more data efficient, more accurate, and better at making long-term predictions, especially for complex systems.
Exactly. It's a win situation.
Yeah, those are some huge advantages. Now, you mentioned a table that summarized these different architectures, right?
Yeah. Table 1 gives a nice overview.
Can you break that down for us?
Sure. First up, we have the HNNs. Their key feature is energy conservation. They can handle non-separable Hamiltonians and are good at modeling things from simple pendulums to more complex systems. And their main advantage is learning these conserved quantities without needing specific instructions.
Gotcha. Then we have the SympNets.
Yeah, SympNets are all about preserving that symplectic structure. They also handle these non-separable Hamiltonians and have been used for a bunch of different Hamiltonian systems. The main thing here is their ability to preserve that volume in phase space and approximate those symplectic maps.
Okay, and then SympFlow.
SympFlow adds that idea of a time-continuous flow while still being able to handle those non-separable Hamiltonians. It's been used to model all sorts of systems, from chaotic to dissipative ones.
Very versatile.
Yeah, and the main benefit is being able to get predictions at any time point and even potentially figure out that Hamiltonian function.
Awesome. And last but not least, MetaSym.
MetaSym brings meta-learning into the mix. It can handle those non-separable Hamiltonians too, and has been used for things like spring meshes and even open quantum systems. It's really good at generalizing across different but related systems and modeling forces that don't conserve energy.
Got it. That table really paints a clear picture of these different physics-informed networks. It's pretty amazing how we can use these fundamental mathematical and physical ideas to create such sophisticated AI.
Okay, let's switch gears completely and dive into something a lot more abstract, category theory.
Okay, so category theory.
Yeah, how does this super abstract math even connect with deep learning? It seems like a world away.
It might seem that way, but there are some really deep connections. Category theory is all about understanding structures and relationships in a very general way. Instead of looking at specific mathematical objects, it looks at the connections between them.
So it's like looking at the blueprint of how different concepts connect rather than the concepts themselves.
Exactly. And the basic building blocks are categories.
Okay.
They consist of objects, which can be anything from sets to neural network layers, and morphisms, which are like arrows connecting these objects.
Arrows.
Yeah. And these arrows have to follow certain rules.
Okay.
Each object has an identity morphism, basically an arrow that does nothing.
And you can combine morphisms, and the order doesn't matter.
Interesting. So we have these objects and arrows with specific rules. What other big ideas from category theory are relevant to AI?
There are a few. Functors, which are mappings between categories that preserve structure, so like translators between different categories.
Okay.
Monads, which are ways to structure computations, really helpful for managing things like the flow of gradients in neural networks.
Gotcha.
And then there are adjunctions, which describe a special kind of relationship between functors.
Okay, so it's all pretty abstract.
Yeah.
How does this high-level math actually help us design or understand AI models?
It gives us this powerful language to reason about how we design, put together, and optimize these complex AI systems.
Okay.
It helps us see patterns and relationships that might be totally hidden if we just think about individual neurons or layers.
Right.
And even these things called monoidal categories, which are ways of combining objects, they're being used in things like quantum natural language processing and formalizing this idea of compositional intelligence.
Compositional intelligence.
Yeah, it's about building AI systems from smaller, more fundamental pieces, like building with Lego bricks.
Oh, interesting. And category theory provides the rules for how these pieces fit together.
Exactly. And it can help us understand why certain architectures, like convolutional neural networks for images, work so well. It also gives us a blueprint for designing new architectures that exploit different types of symmetries in other types of data.
So instead of just randomly stacking layers, category theory gives us a more organized and principled way to think about their interactions.
Exactly. And it can even help us understand the learning process itself.
Oh, wow.
Things like categorical optics and integral transforms are being used to model how this gradient-based learning works, giving us new insights.
Okay.
And for compositional intelligence, category theory and these things called string diagrams give us a formal way to combine these basic building blocks.
So we can create AI with better reasoning abilities, and that's easier to understand.
Yeah, exactly. And functors are key here because they let us connect different levels of abstraction in a network, ensuring that the structure of the data is preserved as it flows through.
So it's like building a multi-level structure where each level communicates effectively with the others.
Yeah, that's a good analogy. And this approach allows for more systematic ways of connecting the weights in a network and designing entirely new architectures based on these structural principles.
It sounds like category theory provides a kind of mathematical blueprint for building more organized and understandable AI. You even mentioned it could help bridge the gap between symbolic AI and subsymbolic AI. That's been a huge challenge.
It really has. Symbolic AI deals with abstract symbols and rules, while subsymbolic AI, like deep learning, learns patterns from data. Category theory might be a common language for both.
Okay, I'm intrigued. How's
By representing both the abstract structures of symbolic systems and the processes of neural networks within this categorical framework, we might be able to create AI that can both reason logically and learn from data.
That would be a huge breakthrough. So we could potentially get AI that can explain its reasoning in a way we can understand.
That's the idea, making these models much more transparent.
Fascinating. Do you have a real-world example of how category theory is being used right now? You mentioned supply chain optimization.
Yes, that's a great example. Categorical decomposition can be used to break down a complex supply chain into smaller parts, like demand forecasting, logistics, inventory. Each part becomes an object in a category.
And the interactions between them become the morphisms, those arrows.
Precisely. And then we can use these things called commutative diagrams to make sure everything is consistent and flows smoothly.
Okay.
Plus, we can use monadic structures to handle how things like inventory levels change over time. The benefit is that you get these more modular and flexible supply chains that are also easier to understand.
So even something as practical as a supply chain can benefit from this abstract math.
Absolutely. It provides a clearer and more robust way to understand and manage that complex system.
Okay, we've gone from the world of physics to pure math. Now let's move on to geometric representation learning, which uses Lagrangian and Riemannian geometry.
Sounds like we're back to shapes and spaces.
It does. So let's start with these Lagrangian submanifolds in symplectic geometry. You mentioned this earlier when we were talking about those SympNets.
So a Lagrangian submanifold is a special kind of space within this symplectic structure. Its dimension is exactly half of the total space, and the symplectic form, which is like a mathematical operation, vanishes on it.
Vanishes.
Yeah, it basically becomes zero. This limits the degrees of freedom in that space in a way that aligns with how physical systems with conserved quantities behave.
Okay, I'm trying to picture this. What does it mean for how we represent data in machine learning?
It's still early days, but the link to these symplectic structures and Hamiltonian dynamics suggests that these Lagrangian submanifolds could be really useful for encoding data that has these underlying mathematical properties.
Data that evolves according to physics,
Yeah.
where energy and that symplectic structure are important.
Exactly. Representing this data within or in relation to these submanifolds could help us preserve key features, leading to more meaningful representations.
So it's about finding the right kind of geometric space to represent our data.
Precisely. It's about respecting the inherent structure of the data.
Great. Now let's talk about dimensionality reduction and manifold learning.
Sure.
When we have data with tons of dimensions, it's super hard to analyze. So dimensionality reduction tries to find lower dimensional representations that still capture the important stuff. And manifold learning is based on this idea that high dimensional data often lies on or near a lower dimensional manifold, which is like a curved surface within that high dimensional space.
Yeah, the crumpled piece of paper in our 3D world, which is actually a 2D surface. Manifold learning wants to flatten it out while keeping the connections intact.
Perfect analogy.
Yeah.
So the goal is to minimize distortion when we map the data onto this lower dimensional space.
Exactly. And that's where Riemannian geometry comes in. It provides a framework using these things called metric tensors to define distances and angles not just in flat spaces, but on these curved manifolds.
So we can accurately measure things even when the data is curved?
Exactly. And manifold learning becomes about finding mappings between these Riemannian manifolds that preserve the distances between data points as much as possible.
So Riemannian geometry gives us the tools to preserve the data's inherent shape even when we reduce its dimensions.
Precisely. This is super important for developing good dimensionality reduction techniques, especially for complex data sets.
Okay, so how are these ideas from Lagrangian and Riemannian geometry being used in AI applications today?
In 3D shape modeling, Lagrangian representations like text sphere splatting are being used to get really high-quality representations that are also very efficient in terms of storage.
Wow.
In fluid dynamics, Lagrangian methods are used to track how fluid particles move. And we're seeing these Lagrangian flow networks that can model fluid behavior while respecting conservation laws. And for data that naturally exists in curved spaces, like hierarchical data, researchers are using embeddings in hyperbolic and spherical geometries.
Interesting.
There's also work on learning representations for things like polygons and trees. And a project called DocGeoNet uses geometric priors to improve document image rectification.
So geometry is becoming a key tool for handling complex and structured data in AI.
It's helping us see the shapes and relationships in a more natural and insightful way.
Okay, our last stop on this deep dive takes us back to physics with the concept of symmetries, conservation laws, and Noether's theorem.
This is one of the most elegant and profound results in physics.
I know, it's mind-blowing.
Yeah.
But for those who need a refresher, can you explain what Noether's theorem is all about?
Sure. Noether's theorem basically connects the symmetries of a physical system to the quantities that stay constant within that system.
Symmetries like what?
Think about the laws of physics. They don't change over time. That's a symmetry.
Okay.
And that symmetry directly leads to the conservation of energy. Similarly, the laws of physics are the same no matter where you are in space. That leads to the conservation of momentum. And the laws are also the same no matter how you rotate a system. That leads to the conservation of angular momentum.
It's like a hidden code of the universe.
It's this deep, beautiful connection between the structure of the universe and the fundamental laws that govern it.
Okay, so how is this being applied to AI?
Researchers are finding that this connection between symmetries and conserved quantities can help us build better AI models, especially for understanding physical systems. One way is to have the model learn these conserved quantities directly from data.
So it figures out what stays constant as the system changes.
Exactly. It's like the AI is uncovering the hidden symmetries of the system just by observing how it behaves.
Amazing. And this leads to models that are more accurate and easier to interpret.
Yes, and they generalize better to new situations because they've learned the fundamental rules of the game.
You also mentioned something called Noether's razor.
Noether's razor is a method that uses Noether's theorem to find the symmetries and conserved quantities in a system. It uses Bayesian model selection to favor the simplest explanations.
Like Occam's razor, right? The simplest explanation is usually the best.
Exactly. And the neat thing is that this method automatically embodies that principle.
Cool. So has this Noether's razor actually been used successfully?
Yes, it's been applied to various systems like interacting oscillators and the n-body problem.
The n-body problem, that's like predicting how planets move around a star, right?
Exactly. And the results show that this method can actually learn the correct conserved quantities and identify the symmetries that govern these systems.
So we're really getting AI that can understand the fundamental principles at play.
That's the goal, moving towards deeper levels of understanding. It's all about moving beyond simple pattern recognition and building AI that truly understands the world it's learning from.
AI that's not just better at specific tasks, but is more robust, more interpretable, and capable of tackling really complex problems. Maybe intelligence isn't just in our heads, but exploring these distributed biological systems give us new ideas for designing AI. Maybe these ideas of structure, symmetry, and preservation aren't just shaping AI, but they're fundamental principles that govern complex systems everywhere.
This also reminds me of precision dimension. Have you ever thought about how we can even begin to grasp a number, like pi?
Yeah.
Or the square root of 2?
Yeah. Wow. I'm trying to picture this.
This idea of a precision dimension.
That's right.
What I think is so interesting is this isn't just some abstract math puzzle. This gives us a whole new way to think about some really fundamental questions.
Yeah.
Like, what are numbers really? And how can we even begin to understand those infinite, non-repeating decimals that we call irrational numbers?
Those are tough ones.
All right, so our goal is to understand this theorem and this idea of a precision dimension without getting bogged down in a bunch of equations.
Gotcha.
We want to make these ideas clear and interesting,
Yeah.
and hopefully you'll have one of those aha moments.
Yeah, that'd be great.
So we're talking about using something very specific and countable, like prime numbers,
Okay.
to grasp this continuous and seemingly infinite world of irrational numbers. Okay, so to start this off, the first piece of this puzzle is something called a linear congruential map.
Okay.
What in the world is that? And what are these fixed points we keep hearing about?
So a linear congruential map
Okay.
is actually pretty straightforward.
Okay.
It looks like this. We take a number, we multiply by prime number, and then we're only interested in the remainder after we divide by 1.
Oh, yeah.
We write that mathematically as x, bod 1.
All right, so that mod 1 is just giving us the fractional part.
Right.
Okay, so now what's a fixed point in this context?
So a fixed point in this context
No.
is a specific value of x that when you plug it into this map, you get the same value back after taking the fractional part.
Okay, so the transformation basically leaves this point where it is?
Yeah, exactly.
So the sources talk about this set of fixed points, and they call it SP.
Yeah.
What does that set actually look like with numbers?
Okay, so for a given prime number,
Mm-hmm.
the set of fixed points is defined as k and k0, 1 pedo 2 dots p2.
All right, so let's look at a specific prime number as an example.
Sure.
How about PA5?
Then p1 is 4, and the fixed points would be 04, 14, 24, and 34.
Okay, I see.
And notice how the numerator goes from 0 all the way up to p2,
Okay.
which in this case is 3.
So for PO, we get 0.25, 0.5, and 0.75, all evenly spaced between 0 and 1. Now, what happens if we pick a different prime number?
Okay.
So if P1 is 6,
Right.
and the set of fixed points would be 0, 6,
Okay.
16, 26, 36, 46, and 56.
So again, 6 evenly spaced numbers between 0 and 1.
Exactly.
So there seems to be a pattern emerging here.
Yeah.
For every prime number we pick,
Yeah.
we get evenly spaced numbers between 0 and 1.
And a number of points we get is P1.
Yes.
So the bigger the prime, the more points we get.
Okay, so we're building these sets of rational numbers
Yeah.
that are tied to prime numbers.
Okay.
Now, the next important idea is this meshed size.
Okay.
What is that?
So the mesh size,
Okay.
which we can call deltap,
Okay.
is simply the distance between any two neighboring fixed points within a set. And
Okay.
you might have already noticed
Yeah.
that this distance is always fract1, right?
Okay.
So if you divide the unit interval from 0 to 1 into P1 equal pieces,
Okay.
each piece is going to have a length of 1 P1, right? So for P5, the mesh size is 14,
Right.
and for P7, it's 16.
Exactly.
As the prime number gets larger and larger,
Yeah.
the mesh size gets smaller and smaller.
Uh-huh.
So those fixed points within the set get closer and closer together.
Precisely.
Now let's think about this set that's made up of all the fixed points from all of the sets for
Right.
every single prime number.
So all the fixed points we can possibly make.
Yeah, exactly.
Right.
So the question is, how dense is this set of points within the interval from 0 to 1?
Right.
And this brings us to this idea of density.
Yeah.
What does it mean for a set of numbers to be dense within a certain range?
Well, a set is considered dense in an interval if, for any point in that interval, you can find a point in your set that's arbitrarily close to it.
Hmm.
In simpler terms,
Okay.
pick any number between 0 and 1.
Okay.
Maybe it's a really complicated irrational number with an infinite decimal expansion.
Okay.
Now, if you zoom in closer and closer on that number,
Okay.
no matter how tiny that window is,
Okay.
if the set is dense, you'll always find at least one of these rational numbers from our sets
Okay.
inside that window.
So that means we can get really close to any number in that range,
Yeah.
even irrational numbers.
That's the idea.
So how do we actually prove that this set is dense?
Okay, so imagine you have a target number.
Okay.
We'll call it x,
Okay.
somewhere between 0 and 1. It can be
Okay.
anything.
All right.
Now, you decide how close you want to get to that target number.
Okay.
We can call that desired level of accuracy,
Oh.
epsilon.
Okay.
Think of epsilon as a really tiny positive number.
Okay.
The key here is that you can always find a prime number
Okay.
that's so large that the spacing between its fixed points,
Okay.
which is 1p1,
Okay.
is smaller than your desired accuracy, epsilon.
Okay, so if those gaps between our special fractions are smaller than the margin of error I want,
Exactly.
then we're going to land really close to that target number.
Exactly. And because those fixed points are evenly spaced,
Yeah.
the closest fixed point to your target number will never be more than half of that spacing away. Now, because we chose a prime number where 1p1 is less than epsilon,
Okay.
then frac 2p1 is less than. So that means the distance between our target number and its nearest prime-based fixed point
Okay.
is definitely less than our allowed error.
So no matter what number I pick between 0 and 1,
Yeah.
and no matter how small of an error I allow,
Exactly.
we can always find a prime number and a fixed point from our set
Yeah.
that gets us within that tiny distance from the number.
You got it?
So that means the set must be dense in the interval from 0 to 1.
Precisely.
That's pretty cool.
It's pretty neat.
So it's really the huge number of prime numbers out there
Yeah.
that guarantees we can always find one that gives us the accuracy we need.
That's a good way to put it. So the material we looked at
Yeah.
talks about each prime number adding a new layer of rational approximations.
Right.
And the resolution of that layer is...
I like that image of layers.
Yeah, it's elegant.
It's like we're uncovering new layers as we go deeper.
Yeah.
And getting closer to the true value of any number.
Exactly.
It's like when you're drawing a curve with straight lines.
Okay.
If you only use a few long lines, the curve is going to be really rough.
Yeah.
But if you use more lines and make them shorter,
Yeah.
the curve will be smoother.
It'll be a better approximation.
Exactly. In our case, the primes are like the lengths of our lines.
I see.
They determine how far apart our rational approximation points are.
That's a good way to visualize it.
So we have this amazing tool in prime numbers that lets us zoom in on any number with as much detail as we could ever want.
And it all comes down to the density of those fixed points.
It's not just that we can get close to these numbers with decimals.
Right.
We can do it in this structured way based on prime numbers.
Yeah, it's really fascinating.
So it feels like this isn't just a neat mathematical trick.
No, it's not.
You seem to be some deeper connections here. What are some of the bigger implications of this idea?
One big implication is this concept of discrete approximation of the continuous.
Okay.
Now, the set of all rational numbers actually has a size of 0 in a certain mathematical sense, but their density and this special prime-based way of getting that density allows us to approximate continuous values as closely as we want.
So we can use something discrete, like these special fractions, to understand something continuous, like the real number line.
Exactly.
That's really interesting.
It is.
The material we looked at also mentions something called structured space filling.
Yeah.
How does this prime-based method relate to space filling?
So when we usually talk about space-filling curves, we think about these continuous curves, often fractal-like curve, like the P&O curve or the Hilbert curve.
Okay.
These curves can actually pass through every single point in a multidimensional space.
Wow.
Our prime-based method is a different way to think about filling the unit interval. Instead of one continuous curve, we're using a bunch of these maps, each defined by a prime number, to make a really dense set of points within the interval. It's a filling process that's based on separate points at each step. Because we're dealing with a limited set of rational points for each prime.
Right.
But it's also hierarchical in that each larger prime builds upon the sets created by smaller primes, giving us more and more detail.
So instead of one continuous curve, we have this ever-growing collection of points that become dense in the interval.
That's a good way to think about it.
It's like building up an image with smaller and smaller pixels.
Yeah, that's a great analogy.
Now, to help us really understand this, the source we looked at gives an example of approximating the fractional part, which is about 0.236066797.
Yeah, a classic irrational number.
So can you walk us through how these prime-based fixed points get us closer to this number?
Absolutely. So let's start with a small prime number, like P5. The fixed points for P5 are 0.25, 0.5, and 0.75. The closest one to 0.2361 is 0.25. The difference between those two is about 0.0139.
So not too bad.
Not bad at all.
It's like trying to hit a bullseye with darts. Throwing more darts makes it more likely you'll get close.
Yeah.
But any single dart might be farther away than a previous dart.
Exactly.
It's the overall distribution of darts that matters.
Right.
So going back to our example, what if we use...
So the fixed points are multiples of 110. The closest one to 0.2361 is 0.2. The difference is about 0.0361.
So better than P7?
Yep.
What about a much bigger prime number?
Okay, let's try Phi03. The fixed points are multiples of 142. One of those is 2020, which is about 0.2381. And the error is only about 0.00000.
Wow, that's much better.
Much closer.
What about an even bigger prime number?
Okay, let's go really big. P421. The fixed points are multiples of 1420. And 99420 is about 0.2357. That's really close to our target number.
Yeah, the error is only about 0.0000038.
Extremely close.
So even though using a bigger prime number doesn't always make the approximation better immediately, overall, using bigger prime numbers lets us get closer and closer to that irrational number.
Exactly.
So it's this infinite ladder of prep numbers that lets us refine our approximation.
And that's the essence of the precision dimension. It's this idea that we can keep getting more and more precise as we consider more and more prime numbers.
Now, there's another interesting aspect mentioned in the material,
Like,
the role of prime gaps. What are prime gaps?
so a prime gap is just the difference between two prime numbers that are next to each other.
Okay.
For example, the first few prime numbers
Mm-hmm.
are 2, 3, 5, 7, 11, and 13.
Okay.
The gap between 2 and 3 is 1.
Okay.
The gap between 3 and 5 is 2,
Okay.
and so on.
Okay.
What's interesting is that these gaps can be all sorts of sizes.
Okay, so they're not all the same.
No, they're not.
Okay.
And as we look at bigger and bigger prime numbers,
Okay.
the gaps can get really big.
Wow. So how does this uneven spacing of prime numbers affect our approximations?
Let's think about the accuracy of our fixed points.
Okay.
The first prime number gives us an accuracy of 1p11.
Okay.
Second prime number gives us an accuracy of 1p21, and so on,
good.
where p1, p2, p3
Mm-hmm.
are just the prime numbers in order.
Okay.
If the gap between two prime numbers is small,
Okay.
the improvement in accuracy will also be small.
Okay.
But if there's a large gap,
Okay.
we have to go much further down the list of primes
Okay.
to get a significant improvement in accuracy.
So prime gaps affect how quickly our approximations get better.
Exactly.
If the gaps are small, the improvements are gradual.
Uh-huh.
But if the gaps are large,
Yeah,
we get these big jumps in accuracy.
that's right.
And the material also mentions this idea of entropy or unpredictability
Yes.
in the sizes of prime gaps.
Yeah.
How does that play into all of this?
So prime gaps don't follow a simple pattern.
Okay.
We know that prime numbers become less common as numbers get bigger, but it's really hard to say exactly where the next prime gap will be and how big it will be.
So it makes it harder to find the best prime number
Yeah.
to get a good approximation for a specific number.
Exactly.
It's like the prime numbers are giving us this framework for approximations, but they're also throwing in some randomness.
Yeah, it's a bit of a mystery.
Okay, so this prime-based method isn't the only way to approximate irrational numbers.
Yeah, there are other ways.
The research we looked at briefly mentions Dirichlet's approximation theorem and this concept of continued fractions.
Uh-huh.
Can you tell us a bit about those?
Sure. So Dirichlet's approximation theorem is a really important result in number theory.
Okay.
It tells us that for any irrational number, there are infinitely many fractions that are really good approximations.
Okay.
These fractions are so good that they satisfy a special inequality, xpq1q2.
Okay, so there are always good rational approximations for irrational numbers?
Exactly.
And what about continued fractions?
Continued fractions are a really neat way to find the best possible rational approximations for an irrational number.
Okay.
The convergence of a continued fraction give you the closest fractions you can get
Okay.
for a given size of the denominator. They're considered the gold standard for rational approximation.
So how does our prime-based method compare to these other techniques?
So our method only uses fractions with denominators of the form p1, where it's a prime number.
Okay.
This means we might not get the absolute best approximation for every possible denominator. Continued fractions are better at that.
Right.
But our method still lets us get arbitrarily close to any irrational number
Okay.
by using bigger and bigger prime numbers.
So it's a different approach,
Yeah,
but it still achieves the same goal of getting really accurate approximations.
exactly.
So continued fractions might give you the most efficient approximations,
Right.
but our prime-based method is more structured,
Yeah.
and it's connected to these fascinating prime numbers.
It's a different perspective on the same problem.
Stuff that hides some surprisingly intricate mathematical structure underneath.
One of the really interesting things here is how the source material draws a really interesting parallel here to how in digital computation we have these discrete levels of information,
Right.
like bits that can be either 0 or 1. And there's even this loose analogy to quantum mechanics where you have these allowed and forbidden energy states. It's like only certain specific values are permissible.
Now, the source material takes an interesting turn here, going to prime numbers and entropy.
It is an interesting jump.
Yeah, so how do these concepts even connect?
It's a fascinating and maybe unexpected connection. The source introduces this idea of a prime gap entropy correspondence, or PGEC for short, as a sort of framework for thinking about all of this.
Okay.
And the basic idea here is that prime numbers, being those fundamental building blocks of all other whole numbers, might actually impose some fundamental limits and introduce a degree of inherent complexity to the world of numbers.
So prime numbers are setting boundaries. I'm intrigued. How does that work?
Let's think about the gaps between consecutive prime numbers, the prime gaps.
Okay.
After our initial primes 2 and 3, the smallest gap you'll ever find is 2. The famous prime number theorem, which tells us about the distribution of primes, says that on average, these gaps tend to get bigger as you go further out on the number line, roughly at the rate of the natural logarithm of the number. However, and this is where it gets interesting, their distribution is also incredibly irregular and structured, and this fact is actually deeply connected to the Riemann hypothesis.
So what's the main point that the source material emphasizes about these gaps between prime numbers?
The crucial insight is that because these prime gaps never completely disappear, number space, in a sense, isn't perfectly smooth and continuous. Think of the primes as a kind of scaffolding for all the other numbers, and the gaps between them mean you can't just make infinitely fine divisions when you're building things out of these fundamental units.
I see. So I don't know if this analogy works. It's like trying to build a wall with mucks. You can't make the wall perfectly smooth because you're limited by the size of the bricks and the mortar in between them.
Exactly. That's a perfect analogy.
Yeah.
So this inherent chunkiness in the primes, if you will, introduces a kind of fundamental granularity, a graininess to numbers, to the number line.
Okay.
Now, the source brings in the idea of entropy, which might seem like a jump, but bear with me.
Entropy, like disorder.
Exactly. Entropy, in a general sense, is often thought of as a measure of disorder or randomness in a system.
Okay. Yeah.
And in this case, the idea is linked to the irregular yet structured distribution of these prime gaps. So the source introduces this idea of a prime gap entropy function, H-gap, and suggests a universal entropy floor, SMINDWay H-cap 0. In simpler terms, this means that because of the unpredictable yet strangely ordered nature of prime gaps, any system that's based on numbers can't have zero entropy. There's always going to be some inherent level of randomness or complexity woven into the fabric of numbers.
And this prime gap entropy correspondence, the PGEC, this is the idea that there's a fundamental limit to how much we can compress information because of these prime gaps. We can only simplify things so much.
That's the idea. Now, it's really important to emphasize that this is a highly speculative idea.
Right.
But it's an incredibly fascinating perspective on just how deeply fundamental number theory might actually be.
If I understand it correctly, modular quantization is a way of taking systems that seem continuous and forcing a kind of discreteness onto them using modular arithmetic. It's like setting up rules based on the remainders you get after division, which forces things into specific categories or states.
Exactly. Using these things called residue classes, which are just the remainders you get after division, we can define these constraints.
Right.
And when you use a prime number as your modulus, the thing you're dividing by, these structures can act as quantization conditions, forcing the system to snap into specific allowed states. Now, if we connect this back to our initial discussion about fixed points, remember how the mod 1 part of our transformation was key. That modular operation essentially takes this continuous range of numbers between 0 and 1, and through multiplication by p, it creates a partitioning into evenly spaced rational numbers. And this is, in essence, a quantization effect happening within this continuous interval.
So the modular arithmetic is acting like a filter. It's like a sieve, only allowing certain specific values to pop out within that continuous range.
Precisely. Now, using these prime-based rational divisions to approximate irrational numbers, the concept of a precision dimension, which is a really elegant way of thinking about getting closer and closer to those numbers that can't be perfectly expressed as fractions.
By creating a sequence of these partitions using larger and larger primes, we can essentially fill that interval between 0 and 1 with these rational approximations that get increasingly close to any number, even those tricky irrational ones.
Exactly. The source uses a great example of trying to approximate the fractional part of the square root of 5, which is, of course, an irrational number. No matter how close you want to get, you can always find a prime p large enough that one of the rational numbers in the form of key p1 will be within that desired level of accuracy.
So it's like we're climbing this ladder of prime numbers, and with each rung, each higher prime we use, we get this enhanced ability to pinpoint any number on the number line with a rational approximation.
And this idea of a precision dimension really helps to visualize this. It's not just about getting closer and closer in a simple one-dimensional sense. By going to higher primes, we're essentially moving into a space with higher and higher levels of precision in our approximations.
Okay, so now for the part that I know is highly speculative but also super intriguing, the potential connection to the Riemann hypothesis.
This is where the source material gets very careful, emphasizing that these are still early ideas, very much in the realm of speculation. But the core idea is that this process of hierarchical refinement using prime numbers and its connection to what are called cyclotomic structures might somehow mirror or encode the complex oscillations of the Riemann zeta function.
Okay, oscillations in what sense? Can you unpack that a little bit?
Sure. The hypothesis is that the zeros of the zeta function, those special points in the complex plane where the function equals 0, might actually correspond to points of destructive interference in these prime-driven oscillations. Think of it like waves canceling each other out at certain frequencies.
Oh.
That's the analogy being suggested here.
Okay, that's a really interesting visual. And what about the critical line in the complex plane? That's where all the non-trivial zeros are thought to lie, right? How does that fit into this?
The source suggests that this critical line might actually emerge as a natural point of balance or symmetry in this prime-based refinement process. It's like the axis around which these oscillations are most fundamentally structured.
Okay.
And that structure leads to the appearance of these zeros along that line.
So is the idea that because of this infinite hierarchical refinement process that we've been talking about, the zeta function evaluated at a prime number might be forced to get arbitrarily close to 0?
That's what's being suggested, yeah. And this is where the Euler-Maclaurin summation formula comes into the picture. This formula is a really powerful tool in mathematics that lets us connect a sum over discrete values, like the powers of prime numbers, to an integral, which operates over a continuous range. And this connection could help to reveal the underlying behavior and the patterns of interference related to how the zeta function behaves in the complex plane.
Okay, so how does that cyclotomic factorization fit into all of this? The source material talks about that too.
Cyclotomic polynomials are very closely related to the roots of unity, which are those complex numbers that, when you raise them to a whole number power, give you 1. They represent these very fundamental periodic patterns in mathematics. And the fact that we can factor pk1 into these cyclotomic components suggests that this process of refining things using prime powers is inherently introducing these periodic oscillations, which, as we've discussed, could hold the key to understanding those intricate patterns of the zeta function.
Wow, okay. And to capture all of this, there's that pretty intense looking equation. It's a bit of a mouthful, but can you break down what it's trying to say?
That equation, despite its intimidating look, beautifully encapsulates this idea. For every prime number, p, and each of its powers, k, we have a product of terms that involve these complex exponential functions, the ones at the heart of the roots of unity. And the underlying idea is that the precise way all these oscillations, these patterns, interact across the entire hierarchy of primes and their powers is what gives rise to the zeros of the Riemann zeta function.
Okay, so we ventured into the speculative yet utterly fascinating realm of a potential connection between all of this and the Riemann hypothesis. It's still early days for these ideas.
Very early.
But it's truly mind-blowing to think that something as seemingly simple as the gaps between prime numbers might hold clues to solving one of the biggest mysteries in mathematics.
Absolutely. It really highlights the deep interconnectedness of different areas of mathematics, and it makes you wonder if the structure of prime numbers, these basic building blocks of arithmetic, could actually be underpinning some of the most profound and challenging problems in math, and maybe even physics.
That's an incredible thought to leave our listeners with. Thank you so much for taking this deep dive with me, and thank you all for listening. We hope this has sparked your curiosity and given you a new appreciation for the hidden beauty and the intricate connections in mathematics. Until next time, keep exploring.